Today we will discuss Rolle's theorem and the mean value theorem. They are very similar, okay? That's why they're grouped together. To start out, I have this graph up here with coordinates A and B. I would like you to draw 3 different graphs that are continuous and differentiable that all pass through A and B. I don't care what they look like as long as they're continuous and differentiable. And what I want you to look at, what is one thing that all 3 graphs have? The end behavior is the same. Okay.
They all pass through A and B.
Okay, well, if you drew a straight line, your slope would be 0. Okay, if you drew a curve, I would say no, because you're probably not going to always draw at a constant rate. Like, I could draw this that would not have an average of 0 slope. But you have part of the right idea. Not the part that I want. Okay? Okay. Between A and B, you either connected the 2 dots with a straight line, or you did what? Or you went up and then back down, or down and back up.
Yes.
In any instant, in either of those 3 cases, right, either you had this, all right, or you had this, or you had this. There's a similarity with all 3 curves. I'll give you a hint. It has to do with a derivative.
They all have a point where the derivative is 0.
Perfect.
Oh yeah.
Okay. Each one of them has a point where the derivative is 0. Why? Does that make sense?
There's at some point the derivative has to change if it's going up, and if it's a straight line, it's always 0.
Okay, well, first off, I connect them with a line that has a constant slope of 0, the derivative of 0 at all points. Okay? Okay. If we're increasing at A, we're eventually going to have to decrease to get back to B, or vice versa with decreasing and increasing, right? So at some point, our derivative is going to be 0. Meet Rolle's theorem. Okay? If we have a function continuous on the closed interval and differentiable on the open interval, and we know the y values at A and B are the same, just like in our picture, then at some point there has to be an x value c where our derivative is 0. So continuous on the closed interval, differentiable on the open interval. Our y values are the same for A and B. Then there has to be at least one number where our derivative at that point is 0. There could be more than one, but there has to be at least one. The stipulations of being continuous on the closed interval and differentiable on the open interval is very important. If our function does not meet these two stipulations, then we can't use Rolle's theorem. Okay? Now, continuity, what things do we need to look for a function not to be continuous? A whole, asymptotes. Corner would tell us that it is not differentiable at that point. Okay, and asymptotes at low. We can't be differentiable in that. Breaks. Okay, so if we have a piecewise function, we need to make sure that it did not break. Right. Okay. So you have to check to make sure you are continuous and differentiable on the interval, closed or open, depending on which one you're checking, before you actually continue with Rolle's theorem. Because if it doesn't meet those two, we can't apply Rolle's theorem. Okay? So here we go. Show that there must exist a c value where our derivative at that point is 0 in the interval -1 to 3 for x squared minus 2x. Okay, now I want you to, we're going to do this using calculus. We could probably do this by thinking about the graph, because what do we have? We have a graph. Okay, we're going to do it using calculus. All right, so first of all, is it continuous on the closed interval? It is, where it's a polynomial, it's continuous. All right, also, it's a polynomial, so it is going to be differentiable everywhere, but specifically the open interval -1 to 3. Okay? So, now, what is our function at -1? What is our function at 3? Okay. What's our function evaluated at 3?
3.
Okay. So we have the same heights, right? We're continuous and differentiable. So, how are we going to find this c value? Yes?
Take the derivative of the original.
Okay, well, first of all, we want our derivative to be 0. So, let's take the derivative. What's our derivative? 2x minus 2. And we're worried about where our derivative is 0. Which is where? 1. Okay. So our c value that they're looking for is 1.
Why does it matter that we show that the left part if we already know that, like, if we can just evaluate the derivative and see if it has a 0 between the interval?
Well, Rolle's theorem says that as long as our heights are the same, we will have.
So, really, do you need that?
I mean, you probably wouldn't necessarily
If
need
it
to show
says-
this,
Okay.
right? You could probably do this in your head,
And say, like, oh, so I know that this should work out.
right?
Okay.
I mean, Rolle's theorem, yes. The point of Rolle's theorem is that we will definitely have a place where it is 0 because our heights are the same.
Okay.
Okay. This is more just for emphasis. All right. Rolle's theorem, and when we talk about the mean value theorem, will pop up in like AP multiple choice questions. The more I emphasize things like this, I'm hoping the better you'll remember them for when they try to trick you on a multiple choice question. All right. So we have a parabola, right? What did we really just find? We found that our vertex is at x equals 1, right? Because that's where we're changing direction. Okay. All right. Great. Is this a continuous function from -8 to 8?
Yes. That minus 1. Minus L.
1, I promise.
Okay.
What about differentiable?
Yes.
There's a corner
Why?
because that's how those 2/3 into our big
Okay. What is the derivative?
2/3 x to the negative 1/3, so there's going to be 0.
Here's our derivative, which means x to the 1/3 is going to be in our denominator. What can we not divide by? What would make our denominator 0?
0.
Which means we're not differentiable at 0 because it makes our derivative undefined. So since we are not differentiable at 0, we cannot apply Rolle's theorem because 0 is in the interval we're wanting to work with. If we were in the interval 1 to 8, not a problem. -8 to 8, problem. Yes.
But if we were on the closed interval of 0 to 8, would that still work?
That would be okay because it would be differentiable on the open interval. Everyone understand that question?
Yeah.
Okay. So we can't do this.
It doesn't need to be continuous.
And it still would be.
Oh, yeah. it would.
Yeah,
It's
it still would be. Yep. Okay. Now I want to find C values in the interval -2 to 2. That make our derivative 0 for x to the 4th minus 2x squared. Okay. Are we continuous on the closed interval?
Yes.
Or polynomial? Yes. Are we differentiable on the open interval?
Yes.
Yes, it's polynomial. Let's just double check. What is our function evaluated at -2?
8.
And our function evaluated at +2?
8.
Okay, so we're at the same heights. We're continuous and differentiable. We're going to have at least one value where our derivative is going to be 0. What is our derivative?
4x will be minus 2x. Or 4x.
Okay, and we're concerned about where our derivative is. How do we solve that?
You can back out of x and then it's a difference of squares.
Okay. So what do we have?
0, 1.
0, 1, and -1, which conveniently, all three of those fall in my interval. So in our interval, we have 0, 1, and -1. Only give the answers for only give the C values that you get that are actually in your interval.
So on that last one, it said use Rolle's theorem. If we couldn't use Rolle's theorem, we just don't do it.
Right, you say Rolle's theorem can't be applied. Very good. All right. The next thing we're going to look at is the mean value theorem. Mean in math means what? Average. Okay. So I would like you to read this over, look at the picture. So we have the same stipulations. We need to be continuous on the open interval, closed interval, differentiable on the open interval. Okay? Now, in the mean value theorem, it doesn't matter what the heights are. All right? This is saying what? Okay, what is this? This is the derivative. What is this?
The x amount, the difference of the x values.
How many x values are in this slope?
The slope, the average rate of change. Y minus y over x minus x.
Oh, okay.
I thought we
I
were
thought you were talking about
just
the
the
denominator
bottom.
specifically. The slope.
The slope.
Okay, sorry to confuse you. All right, so this is saying that no matter what the height of our points are, at some point our derivative is going to equal the average rate of change, aka the slope. Okay, so here in this picture, yes.
So does this work on things that where Rolle's theorem would apply as well?
We will get there. Okay. Here's A and B. Here is the line connecting them. So here is this is representing our slope, right? Our average rate of change. Here's our average rate of change. At some point along the curve, our tangent line is going to have the same slope. Our derivative is going to be the same as our slope between the 2 points. Do you buy that?
Yes.
For any curve? Who said no? Okay, so Aaron kind of jumped ahead of me. Well,
Dang it, Aaron. Sorry, I was curious.
okay. So the mean in the mean value theorem, okay, which I was trying to get you to say, right? Average, we're looking at the average rate of change, okay? Open your book. There's something on the bottom of page 170.
L7.
I want you to read that paragraph.
Can you read it?
No, just give yourself. Okay. What's that paragraph saying? Okay. Our tangent line is parallel to the secant line. They have the same slope, right? Okay. Everyone okay there? Yes. We really probably summarized it more in our conversation than before you read it, right? We were ahead of the game. Now, Aaron already wants to compare it to Rolle's theorem. How can we make a connection to Rolle's theorem?
Well, if A and B are the same height, then the average slope between them will be 0.
Okay. Okay. So, Rolle's theorem, A and B are at the same height, which means that secant line is going to have a slope of 0. Okay? So Rolle's theorem is just a special case of the mean value theorem. That is nice, right? All right, we're good with that connection? Perfect. Okay. What is the average rate of change of this function in the interval 0 to 1? No. What do we need to find? What's average rate of change? Slope. What is our function value at 1?
2.
What's our function value at 0?
-1.
So we have 2 minus -1 over 1 minus 0, and we get 3. Average rate of change. We all good there? Okay. Keeping that in mind, I want to find a number in our interval 0 to 1 such that the instantaneous rate of change is the same as the average rate of change. Okay? Mean value here. Okay. So what do we need to do?
You set the derivative equal to 3 instead of equal to 0.
So this one. All right, so we need the derivative. Yes. What is it? And instead of setting the derivative to 0, we're setting our derivative to our slope, 3. Which means 2x is 1 and x is 1/2. Is 1/2 in our open interval of 0 to 1?
Yes.
Cut in the middle.
Right? So what does this look like graphically? Okay, we have, what were our coordinates again? 0, 2? No.
0, 1.
0, 1?
Oh, no, 0, 1,
1, 2.
2. 0, -1.
0, -1. Okay, so, should go bigger. 1/2. There's our tangent line parallel to our secant line. Okay, horrible picture, but we get the idea. Okay. All right, use the mean value theorem to find a C for x to the 2/3 on 0 to 1. Okay, so what do we need to do first? Find the slope. All right, function value at 1 minus function value at 0. Our slope is
1.
Oh, what have we not been checking?
You didn't check for continuity or differentiation.
We did not check for continuity. Are we continuous on 0 to 1? Are we differentiable on the open interval 0 to 1?
Yes.
Are we different to what, 0?
No,
But does that matter?
no.
Okay. Whew. Alright, so now that we backtracked, that was supposed to be done first. I got excited, I apologize. We found our slope of 1. Now what do we do with that? Our derivative is
2/3 x, or 2 over s, 2, yeah.
2/3 x to the negative 1/3, which we would write like this, correct?
Yes.
We would like to know where this is 1. Okay? So can I just multiply by x to the 1/3? Cube both sides. 8/27. Does that belong in our interval?
Yeah.
Okay. And then this is where Aaron got excited and asked me a few questions. So here's your homework.